Good morning, ladies and gentlemen. Welcome to the 8th series of Geosynthetic webinar under the theme Use of Geosynthetics in Roadways Founded on Expansive Soils. This event is brought to you by the International Geosynthetic Society Chapter Indonesia or INA-IGS. My name is Rifa Nurkayungyun and it is a pleasure to act as your master ceremony in this event. Before we start, allow me to read the rundown of our event this morning. First, I will be reading the rules of the webinar. Second, there will be an opening remarks by one of the members of INA-IGS, Dr. Insinyur Asriwianti Desiani, MT. After that, the event will be guided by Bapak Michael Dobi as our moderator to start the presentation of our speaker, Jorge Zornberg, Ph.D. PE, FASCE. The event will then continue with a Q&A session. We would like to ask you to stay with us until the end of the event because we will be doing a quiz with the total of 250,000 rupiah for 2 winners. We will also give you access to the e-certificate at the end of this webinar. Ladies and gentlemen, for your own convenience, please put attention to the following rules. You can submit your questions for the speaker through the Q&A feature located at the bottom of the screen. The question should be in English. You can raise your question before, during, and after the presentation of the speaker. We expect you to stay with us until the end of the event to get the information you need regarding the e-certificates and also the soft copy of the presentation from the speaker. This event is also live streamed on INA-IGS YouTube channel, or you can directly go to the link s.id/INA-IGS08YT. If you have any question, please contact Sandy at the numbers shown on your screen or on the chat box. Now, without further ado, I would like to invite the representative of INA-IGS, Dr. Insinyur Asriwianti Desiani MT, to give her opening remarks. To Ibu Asri, the time is yours.
Ladies and gentlemen, I would like to welcome you to INA-IGS Geosynthetic webinar. Today, we will be hearing a seminar from our keynote speaker, Professor Jorge Zornberg, about the use of geosynthetic in roadways founded on expansive soils. As you may already know, geosynthetic is commonly used in road construction, which may be built on expansive soils. Construction on expansive soil is a common sight throughout the world. This is why today's topic is so interesting for us, geotechnical and civil engineers. I would like to thank Professor Jorge Zornberg from the University of Texas, USA, for taking the time to share and discuss this topic with us today, as he is renowned expert on transportation geotechnic and geosynthetic. I would also like to thank all the participants and the organizer of this event. I hope that we all can learn new things and apply them to our own projects and procedures. Thank you, and please enjoy the webinar. Back to you, Rifa.
Okay, thank you, Ibu Asri, for your kind remarks. Ladies and gentlemen, now this webinar will be guided by our moderator, Bapak Michael Dobi. Before I give the floor to Bapak Michael Dobi, I would like to remind you that you can start submitting your questions from now, during, and after the presentation by using the Q&A feature. We would like to also remind you to stay with us until the end of the event to get the information you need regarding the e-certificates and also the soft copy of the presentation from the speakers. Now, please welcome our moderator, Bapak Michael Dobi. To Bapak Michael Dobi, the time is yours.
Thank you very much, Rifa, for your introduction, and also to Bu Asri. I have a great pleasure and honor today to introduce both our guest speaker and the topic. So today we're going to hear, as you've heard from Professor Jorge Zornberg. Before I get into that, I just also like to thank very much our committee that's from the INA-IGS who organize these events, because I think we all know a lot of work goes on behind the scenes to create these webinars. And I feel that they are run extremely smoothly and professionally, and that's all due to this hard work that we don't often see much of, but I can assure you it's going on. So a few words about today's topic. It's actually in this year, during our series of webinars, this is the first time we've had a topic on road pavements. And I think actually that's really important that we are now hearing on such a topic. And in this case, it's specifically the issue of building roads over expansive soil subgrades. Now, you might ask why. Well, you're going to find out why in a minute, and I don't need to tell you any more about that at the moment. I think our speaker will be telling you exactly why this is important here. And certainly our speaker today, Prof. Jorge Zornberg, has extensive experience and knowledge in this field, and we're going to be able to share some of that today. And I think for me, especially, it's a great treat to be able to hear about this kind of information about this particular problem. I've known Jorge for quite a few years now. We tend to meet at conferences and IGS events around the world. I think the last one would have probably been about 2 years ago. Sadly, of course, it's difficult at the moment with our difficult situation with the pandemic going on. I'm very much hope I'll be able to do so again before too long. Anyhow, for this event, I'm going to welcome Jorge to Indonesia for the very first time, unfortunately, in a virtual way this time. He hasn't been to Indonesia before. I'm really hoping very much that we can invite you for a full visit, Jorge, one day before too long. But it's not going to be quite yet, is it? Anyhow, so a few words about Professor Jorge Zornberg. He's a professor at the University of Texas at Austin. You can see on the slide here, he has an extensive list of achievements and honors. I'm going to mention two, which I think are very relevant. First of all, Jorge is a past president of the IGS. He was the one before the last one. And in fact, he's also the third past president to speak to us during our webinar series this year, which is also a great honor for us. He's also a past Mercer lecturer. And again, he's the third Mercer lecturer to speak to us during our series of webinars this year. Now, the reason why I mentioned the Mercer lecture is that one of the targets of the Mercer lecture series, which is in memory of Dr. Brian Mercer, is to make sure that there is connection made between geosynthetics and the underlying importance of the soil mechanics and geotechnical engineering that goes on in the background. And I think today we're going to hear a bit about that. And for me, that always remains a really important part of this type of event. So I think I've just about come to the end of what I'd like to say. I've listened to quite a few of Jorge's lectures and presentations in the past, and what I can tell you is that they are always marked by a combination of passion and enthusiasm, together, of course, with his expert knowledge on the topic. And we're going to have the honor and pleasure of enjoying that today. So, Jorge, the floor is yours for the next hour or so. You've asked me to give you a warning at about 45 minutes, which I will do. And we're looking forward very much to this event.
Thank you very much, Mike. Thank you so much for INA-IGS. It's for me such a pleasure to be here and share some of the experience that I have had over the years, both on geosynthetics and on expansive clays. For me, it's a special treat to be able to share this information. I had the opportunity to look a little bit into the important geography of Indonesia. I just wanted to make sure to understand why expansive clays is an important problem for you, and it really is an important problem. Thank you again for INA-IGS. It's such a pleasure to be virtually, but I am in Indonesia, so I'm so pleased. Let me tell you a little bit about my topic. As it has been mentioned, I'm going to talk about the use of geosynthetics in roadways founded on expansive soils. I'm going to divide this presentation in two parts. The first one is going to be strictly geotechnical. I'm going to tell you a little bit about why do we have a problem. And we do have a problem in the US with expansive clays. We do have a problem in Indonesia with expansive clays. I'm also going to tell you how to characterize this problem. Before coming up with a good solution for a problem, we really need to understand the problem. And I'm going to show you, and it's surprisingly very similar, the way in which we characterize the problem, which is the problem of expansive clays. And then I'm going to tell you about solutions. And when it comes to solutions, I come from a place where we have significant problems in Texas, USA, significant problems on expansive clays. And we have gone through different methodologies to try to solve this problem. I'm going to explain to you how we went from characterizing the problems that we have in the field to understanding properties that matter, to understanding solutions that can be used. So without further ado, let me then start with the problem. What is our problem? And the problem is going to be essentially that of roadways founded on expansive clays. Not only roadways, but any structure, geotechnical structure founded on expansive clays that has comparatively low pressure. That's the case of roadways, that's the case of houses, that's the case of low buildings. Have a problem when the foundation soils are in expansive clays. What is the problem? How do we see that we have a problem? Well, if this is the original ground profile of a roadway, then if this is founded on expansive clays, it's going to happen the following. What does it mean, expansive clays? It means that if we have changes in moisture, then we have changes in volume. During the wet season, things swell, the soil will swell. During the dry season, the soil will shrink. That's not so terrible. What is really bad is that swelling and shrinkage is differential. So for example, and I'm going to put my pointer here. For example, in this particular roadway, we have that the shoulders typically change moisture very quickly. They are exposed to the atmosphere. In a paved road, the center line doesn't change moisture that much. So what is going to happen? Well, during the dry season, the shoulders are going to shrink and the center line will not. And during the wet season, the shoulders are going to heave and the center line will not. Actually, what we have in then is a very mechanical problem. So we have a road that is flexing itself downwards from the edges, and we have consequently a crack that develops longitudinal crack. And during the wet season, the cracks will even close some, but the crack is already there and water already can make its way into the structural portion of the roadway. So we really have a problem. Let me show you a problem as we have it near my home in Austin, Texas. This is what you should expect to see. This is the type of problem that you will see on a roadway that is founded on expansive clays. Do not blame the traffic for this problem. Traffic is not the culprit. Traffic has not created this longitudinal crack. Sometimes we call them environmental cracks. the culprit for this significant damage in our roadways. And we have measured this heaving and shrinkage of the shoulders. In this particular roadway, we had, if we measure the profile in August 2015, August meaning the summer in Texas, then over 3 years, we were measuring how much the shoulders will heave and settle, heave and settle. And yes, only in these 3 years of heaving and settling, we have differential settlements on the order of 3 centimeters. That's a lot. 3 centimeters, and that's not extreme weather conditions. That is the significant differential settlement that happens within the span of the width of a road. How often is this problem? It is very common. It is very common. And here we have a view of a geologic map in the US. Essentially, the entire central US that is colored blue. That means that those units have a significant abundance of expansive clays. If it is painted red, essentially this means just don't build here. Essentially, the abundance of clays is so much that you'd rather don't put your cities in here. Let me show you a little bit more of detail of Texas. Texas is in southern US. And let me show you a little bit of this geologic map in Texas. Remember red, don't build in here. Well, that was not what Texans did. 4 out of the 5 biggest cities in Texas are along this red line, which is the Eagle Ford Formation. So here we have Dallas and Fort Worth and Austin and San Antonio. They are all along the Eagle Ford Formation. So we have a significant problem on expansive clays, and many of our roads are suffering this problem. This is, for example, a view of, some of us would call it the Badlands, the Texas version of the Badlands. And here we have the longitudinal cracks, in this particular case, in San Antonio. This is another view of the problems that we do have in San Antonio as well. These are all from the same region. How bad is this problem? How big of an impact is in the finances, economic impact of having expansive clays? I can tell you, this is very well documented. And actually is documented, the documentation comes from insurance companies. And it's staggering. So here we have in the horizontal axis, 0 to 4, 6, 10 billion dollars. And here different events going from Northridge earthquake, Hurricane Andrew, Loma Prieta earthquake. The annual costs that are incurred because of expansive clays in the US alone is higher than 15 billion with a B dollars. And these numbers, it turns out that this could be considered a natural hazard, the problems associated with expansive clays, periods of heavy rains or unusually very dry periods. And these costs are, in an annual basis, exceed the costs by all other, in average, all other natural hazards in the US. And there are many. There are earthquakes, there are floodings, there are tornadoes. So all those costs, in average, annualized, are not as high as the cost of expansive clays. Now, so we have a problem in the US. But let me tell you something. In Indonesia, you also have a problem. I'm so impressed with this document that I had access to from the Department of Public Works in Indonesia. This document was put together by the team of, as part of an expansive soil survey program very recent, 2019. Honestly, the Dr. Aldiamar and his team should be congratulated for an excellent survey that they have achieved, that have compiled. And this is the initial step for characterizing the problems that I'm going to be showing you. Indeed, this work is so fantastic. There is an atlas of expansive soils that has been recently compiled for Indonesia. Let me show you a little bit of the information. I showed you some of the examples of the maps and the damage that we have in Texas. Let me show you a little bit the map and the damage that you have in Indonesia. This is the map of, in green, you have the location of where there has been damage induced by expansive clays. And you are a nice nation of islands. And as far as I can tell, every single of your islands, every one of your provinces have a problem of expansive clays. This document has been compiled to create this distribution map. And I'm going to show you a little bit about the data that was collected. And this is the first step that is fantastic for a preliminary design phase of any infrastructure that has been that is planned. Why? Because once you know that you have a problem, you need to come up with a solution that is feasible, that is as economical as possible, and that it performs adequately. And that is the objective of this initial program that was compiled so excellently by the Department of Public Works in Indonesia. Very recent again. So let me show you how your roads look like. Let me take you to, I understand that many of you may be in West Java, near Jakarta. So this is what is, remember that I showed you some longitudinal cracks in Texas. These are your longitudinal cracks in Java. And this is also in the same region. You have more longitudinal cracks. You may have two fingerprints are what you will observe the most. One is going to be the generation of longitudinal cracks, and the other is the presence of differential settlements. This is another road, also in this case in Banten, I understand. And here is a third example in West Java, and where you have these significant, to me, they're beautiful cracks, but okay, I know that they create a problem, but we make the point that we know that these soils are founded, these roads are founded on expansive clays, and here we see a very, very similar type of distress in the roads in Indonesia as the ones that we have in Texas. But it's not only in West Java and Banten that you have a problem. You have similar problems in East Java, and you have a similar distress, in this case in West Timor. In this particular case, I noticed that they have quantified. Remember that I showed you the differential settlement on the order of 2 to 4 centimeters differential settlements over the years. Well, here the Department of Public Works also measured the differential settlement along one of these big cracks, 2 centimeters, and the width of these cracks. These are not tiny cracks. These are not fingernail cracks. Here we're measuring 5 centimeters wide longitudinal cracks. And let me take you to Sulawesi. You also will have similar types of distress. Once you have identified that you have expansive clays, unfortunately, the design that we do for roadways is not helpful. Because when we do design for roadways, we design for traffic loads. These are also loads, but some would call them environmental loads. And that is not what we need. That's not what our design methods are prepared for. I'm going to tell you a little bit on how we do the design for expansive clays, roadways in expansive clays in Texas, which, by the way, is similar to some of the guidance that you have from the Department of Public Works. So an additional piece of information also coming from this important document, you will have data from the soils, from soil sampling, with the data that has been collected by your Department of Public Works. In this case, I'm going to remind you about a little bit about geotechnical engineering. What we really need to know about these different clays is their mineralogy. But that's too expensive, that's too slow, that's quantitatively not very accurate. So there are some surrogates, there are some indexes. One of those indexes is called the, is establishing the relationship between the plasticity index in the vertical axis and the percentage or the fraction of clay in the horizontal axis. This is called the activity. The slope of these lines is the activity of a clay. This central line means activity of 1. And just each one of these are data points from South Sulawesi. And essentially all the points, this line corresponds to a slope of 0.5. 0.5 is okay. You do not have such a significant swelling. Around 1, you have a significant problem. Around 1.5, your problem is excessive. And you have some locations with activity that exceeds 1.5. This is an index, but it's a very good initial indicator that you need to do an additional evaluation to see how to design for these problems. So let me tell you, after this initial evaluation, how do you characterize this problem? And again, I'm going to take you out of geosynthetics for the time being. I'm strictly talking about geotechnical engineering. Okay, some of you may remember what is the source of the problem. Why do we have a problem? Why these soils behave this way? Well, it has to do with the mineralogy of the clays. So this is an electron microscope picture of smectite, or some could call it montmorillonite. I'm going to tell you what is the difference. These are smectites, very platy minerals. They are very thin minerals. As a reference, what you see in here is a quartz crystal. This is a quartz, and these are the smectites. These smectites are the culprit for the swelling of the clays. What is wrong with these smectites? Well, it turns out that they are not electrically balanced. All smectites are 3 layers of what is called unit formations on these minerals. This is a mineral called a smectite. Here we have quartz tetrahedrons, and in the middle we have an octahedron. Among the different atoms that we have, and I'm going to take you to your chemistry, we have typically this smectite would be balanced, electrically balanced, if all the central cations are aluminum. But it turns out that over geologic times, there is an abundance of magnesium, and some of this magnesium come and kick out this aluminum. This aluminum, remember, and again, I'm going to try your chemistry, but only the valence in this case. Aluminum has a valence of +3, and they are kicked out of the matrix of these smectites, and they are kicked out by the magnesium. So if we replace atoms that have a valence of 3 positive by atoms that have a valence of 2 positive, we end up with a net negative charge. So these clays are charged negatively, and they are avid to become satisfied, to satisfy the electronegativity of these minerals. How is this satisfied? By attracting cations that are in the water. So these negatively charged clay minerals want water. They want water because with the water come the cations, comes the calcium, and comes the sodium, and comes the potassium that is in this water, and they attract the water. And by attracting they want the cations, and by attracting the cations, they attract the water. And consequently, these clays will swell. If we give them water, they will take water. We give them more water, they will take more water. How much they can swell? Typically, this is limited by how much water they can take. There is a limit, but that limit may be particularly high. So this, and what happens is that if the water is not available, then this interspace, this space between minerals will shrink, and then it will swell, and then it will shrink again. We give them water, they will swell. We eliminate water, but let's say by evaporation, they will shrink. This is characterized. I'm going to take you. I took you through the recent atlas, a very 2019 product of your Department of Public Works. Let me now take you to another document, which is a technical guidance also by the Department of Public Works. And essentially, they provide very similar guidance to the one that we use in Texas. How do we characterize if we have a problem? Well, it turns out that we can measure more beyond the index that we do with Atterberg limits. We can really measure how much clays swell. This is done with conventional tests. Actually, if you're familiar with this test, this is an oedometer. We use it to measure consolidation, but we can use it as well to measure swelling. There's a problem though, and I'm going to show you some results. So these are the results of the Eagle 4 formation. If we put an initially semi-dry, let's say, moist in situ moisture content, a sample of Eagle 4 clay in this case, or of clays from West Java, and then we add water, we are going to have here in the vertical axis swelling versus time. And there will be an initial kind of rapid swelling, and then 1 week it keeps swelling, 20 days it keeps swelling, a month it keeps swelling, perhaps 3 months and still keeps swelling. So this test will take a long time. And more than that, what we need is not just one test. Notice how much it swells, 20%. So if the sample is initially 2 centimeters, if 10 centimeters tall, it will swell to 12 centimeters. Now, this is not only one test that we need. We need 8 tests for different confining pressures. So for example, we need three swelling tests. So it's not only a couple of months long test, but we need multiple tests, because ultimately what we want is this curve, the swell versus load. And the higher the load, the lower the swell. And this is the type of relationship that we'll eventually want. Now, with these curves that take a long time, but they can be obtained, we can answer, for example, a problem that is called the potential vertical rise. And this potential vertical rise is what is suitable to be used in design. What is a potential vertical rise? If we get a boring log, and doesn't need to be a too deep of a boring log, 5 meters or so, that will do the job. And if we get the swelling in each one of the layers along this 5 meter soil column, we can measure, in the event that this location becomes saturated, how much will the ground heave? That is the potential vertical rise. This is still an index, but it's a very well-educated index. So let me tell you how the Texas Department of Transportation, the DOT, Department of Transportation where I live, what do they say? This is coming directly from the PDM, the Pavement Design Manual. Essentially, what the Texas Department of Transportation says is you need to determine the potential vertical rise at your location. And if your potential vertical rise is less than 1.5 inches, 1.5 inches is on the order of 4 centimeters. If your potential vertical rise is more than 4 centimeters, and again, we're talking about not a hypothetical situation in which your soil will become saturated. We'll go from reasonably dry to saturated. If the rise is on the order of exceeds 4 centimeters, 4 centimeters is a lot, but if it exceeds 4 centimeters, you are in trouble. And you need to do something to bring down the potential vertical rise to less than 4 centimeters. That is the guidance. It turns out that you have a similar guidance. Actually, I was reviewing some of your guidance documents from the Department of Public Works, And you use this approach, or at least some of the approaches that are considered for design, is the determination of the potential vertical rise. I only recognize this figure because of the shape. I do not read Indonesian, but this comes directly from the technical document, the guidance for handling expansive clays. And I recognize it so well that I even know where it comes from. Actually, this essentially what this graph gives you for a given plasticity index gives you an initial reference of what is the swelling. So why to take this? Since we're not going to spend 2 or 3 months to get the swelling, okay, let's get the Atterberg limits. That's faster, and let's make a correlation. And if we get in with a plasticity index, this is not directly the potential vertical rise, but it's the initial step to reach that, to measure that potential vertical rise. I know about this graph, and it's used extensively. Actually, it is in ASCE. ASCE is some sort of the guide for the entire US. If it is in ASCE in the US, it means everyone needs to follow it. It is in ASCE. And I know exactly. So I'm superimposing here the graph as presented by in your document, technical guidance, which is also in ASCE. But I can go back to where is this graph coming from? And it comes from just a few correlations. Back in the 60s, 1960s, a gentleman on the name of McDowell noticed that we needed to do better for design, and he established some correlations, but not too many correlations. Remember that I showed you some damage in San Antonio from Texas? Well, these soils come from there. They did something similar to what, much less, but similar to what the Department of Public Works did in 2019 with a survey. They collected the plasticity index. They measured the very time-consuming swelling tests, and they established some correlations between the plasticity index and the shrinkage. They even extended this. This is the original data. Actually, the current ASCE T258, which is referenced in your technical guidance, comes from these original data points that are very limited. So this is where you, as in Texas and many parts of the world, do the design. We measure the swelling, not directly by measuring directly the swelling, but indirectly by establishing correlations with the plasticity index. It turns out that this very important, let me give you some heads up, and this is a geotechnical heads up. This is gonna evolve. This is gonna evolve because there is a new revamping ASCE T258. Let me tell you what I'm talking about. First, let me tell you what are the goods and bads of this approach. Good. Why measuring if my soil is gonna swell 15 centimeters, the potential vertical rise, is that a good measure? This is a very good index. This is a very good index because it has very good practical implications. So the outcome is very easy to grasp by engineers. So if I tell you that this location will swell 15 centimeters and that location will swell 2 centimeters, we know that we have different problems at the location that we have 2 centimeters versus 15 centimeters. Then it accounts for very, very relevant variables. To get this PVR, we need the profile of soil characteristics. We need the initial moisture content. We need the confining stresses. These are all important variables that we need to calculate the swelling. But there are some deficiencies. To begin with, this is based in way too many correlations. I'm not going to get you into the details of the different correlations. The correlations with the Atterberg limits is only one of them. There are several other correlations to go from your Atterberg limits all the way to the PVR. And the correlations are too many and frankly, too old. So it is time, at least in Texas, this ASCE guidance was originated in Texas. So it is time, the time has become to improve this guidance, not the philosophy. The philosophy, I really like the philosophy. I really like the concept of having to quantify how much my soil will swell, and based on that, defining what are the, is a design criterion. The same way that for a slope or for a wall, you have a factor of safety of 1.5. It tells you, gives you a sense on how far you are from failure. This also is an index, but it tells you how far, how big is your problem, and you can correlate that problem, that field problem, with strategies for stabilization. So but there is a solution, and I'm gonna only walk you through 2 slides on this solution that you're gonna see that is coming. And the solution is, okay, wouldn't it be wonderful that instead of my swelling tests taking a month or 2 or 3, it takes half a day or perhaps a day? Well, the solution has come. And how do I do the solution? This oedometer or this permeameter, what about if we put him in a centrifuge? In a centrifuge, essentially what we are doing is we're accelerating the flow process. We're talking about unsaturated soils. We're talking about a very slow advance on moisture. But if we accelerate that advance, the same advance that will take place in 2, 3, 4 months under 1G, the normal acceleration, now we're doing the same, but we're accelerating that process. And in doing so, we can generate the much needed, so here is the swelling curve compared to the same swelling curve. What we're interested is in the maximum swelling obtained using the centrifuge. So the swelling obtained using the slow swelling test, free swell test, is the same as that obtained by the centrifuge, but it's faster. Actually, the results, this is the type of outcome that we need. This is what the PVR correlations are all based on the relationships in the vertical axis, how much swelling we have for each effective stress. So if I have a column of soil, the top of, if the column of 5 meters of soil is all the same soil, the top meter is going to swell much more than the bottom meter. So the higher the confinement, the lower the swelling. And ultimately, we measure the strains, we integrate those strains on the vertical, and we get how much our ground surface is gonna move. So this is an expeditious approach, is highly repeatable. It generates swell data that comes from multiple soil specimens in a single spin. It is a direct measurement. We're no longer establishing correlations from Atterberg limits, which are a good initial basis, but it's just an index. And the results can be readily used for PVR, for the calculation of the PVR. Okay, so this is as much as I wanted to tell you about can we characterize if we have a problem. Your Department of Public Works is doing I was extremely impressed with that survey that has been done. Now that is a survey with Atterberg limits. You have everything that is needed to define the PVR. I just showed you an example of how a more refined PVR, it's not that it's a different index, is also the PVR, the potential vertical rise. It's just that using this approach, you are obtaining it using direct measurement of swelling. Using the charts, you're using correlations that were established back in the days using Atterberg limits. All right, I told you how to know if you have a problem. For example, if I were in Texas, I would know that I have a problem if my PVR exceeds 4. And essentially, I need to come up with a solution. So essentially, at a given site, if my PVR instead of being 4 is 14, there are some approaches to bring down that PVR from 14 to 4. And once I bring it to 4, according to the Texas guidance, that's my design criterion, and I will be able to say, yes, I'm ready. My road has a PVR of less than 4. I have handled the road for expansive clays. Oh, but we have traffic as well. Yeah, that's what we know how to do. We design also for traffic loads and for expansive soils. It's one and the other. And if we satisfy the 2 design criterion, we're ready to go with our design. That's if we have a problem. Now, let's talk about this solution. I'm going to show you about classic solutions on how to handle expansive roadways on expansive clays. And I'm also going to tell you about an innovative solution. It's innovative because, but Texas has been using this for the last 15 years. So it's still innovative, but it's not new. We have enormous field evidence on how this works. And the solution comes from using geosynthetics. So let me step back and tell you, okay, we're done with characterizing. If we have a problem, we did it. Yes, we have a problem. Okay, now I want a solution. Let me tell you about not the solution only to problems associated with expansive clays, but Mike said that this is the first time that you have this lecture on roadways, geosynthetic and roadways. So let me tell you about the universe of solutions that geosynthetics can be used in roadways. And I'm talking about only in the structural package of the roadways. I'm not getting into other aspects, very important, like erosion control and drainage and walls and embankments. No, this is strictly how in the roadway itself, how can I use geosynthetics? And we can use it in many, many different ways. That's an entire different presentation just to tell you about these different applications. I'm going to talk about only one of those applications, but we need to define why do we need the geosynthetic for, and the key, once we know what we want it for, let's say that we want it to stabilize the base material. Then before we get into the properties, we need to identify what are the functions that we need in order to reach those properties. Those functions can be some mechanical functions, separation, or reinforcement, or stiffening. Reinforcement is developing of tension in order to avoid failure, collapse, tension. Stiffening, I'm calling it this way to differentiate it from stabilization as an application, is when what we want is to develop tension, but in order to control the formations. We also have functions that are hydraulic, filtration, and barrier, and drainage. We're not going to get into this entire portfolio of solutions, but I'm going to give you one reference. This is a chart that a table that you cannot read because it's too small of a font, but I'm also giving you an easy to type, or maybe someone can post it in the chat. I'm not sure if I have access to chat. Let me see. Yeah, I have access to chat. So I'm going to put in chat, I'm going to put for you this link, and you will all be able to download this table. 1 second. Here. All right. So I'm going to post in chat to everyone. I'm posting a link, and from this link, you can have access to this table. All right. And I'm not going to walk you through this table, but I think that is a good reference. And all I'm going to tell you is that if you read this table, and again, I'm showing you this following on Mike's comments that you have, this is your first lecture on roadways. You will see that you can use these geosynthetics in roadways for many applications. And I'm just going to list them for you. Mitigation of reflective cracking in structural asphalt overlays. That's a big problem. You can use geosynthetics for that. You can use geosynthetics to stabilize the unbound aggregate layers. You can stabilize the base layer of your roadway. That's a big, important benefit. You can use geosynthetics to reduce layer intermixing. You can use geosynthetics to reduce the moisture in structural layers. You can use the geosynthetics to stabilize, in this case, if you have soft subgrades, and you have soft subgrades in Indonesia. And finally, you can use geosynthetics to mitigate the distress induced by shrink swell soils. subgrades. This is indeed, this is the case for two cases that are very common in which we have volumetric changes. Case number one is the one that we're dealing, expansive clays. There is a problem that you do not have, that is frost susceptible soils. That's also volumetric changes, can also be addressed with similar techniques that the ones that we are going to be discussing now. So out of this entire portfolio of applications, I'm only going to focus on one, and it's going to be this last one. But I'm going to give you a lot of data about this. All right, so let me tell you, oh, by the way, your Department of Public Works also identifies approaches to solve this problem. So we have the identified approaches in your technical guideline document. Essentially think of it, we have a soil that swells, and I want to decrease that potential vertical rise. What can I do? Well, and your guidance says that you can do material replacement. Okay, if the culprit are the top 5 meters, in an extreme, I need to excavate the top 2 or 3 meters and replace it with non-swelling soils. Very often, it's very expensive, but that can do the job. Another solution is to do water management. And in your guidance, you have several strategies on how to use water management. Essentially, do not let the water reach under your roadway. And if the water doesn't reach, the fluctuations of water that cause the problems are not going to be so significant. Texas, and in general in the US, we use this approach, I could say, in the 1990s. But it turns out that water is very smart, and putting controls for water management, the controls need to be done so well. Water can find its way very easily, and we typically do not use the quality control that we need, for example, in waste containment facilities. So it has been too expensive to do it well, and if we do it so, it's not effective. That's the experience learned in Texas. And also stabilization. But in this case, stabilization, again, I'm listing the identified approach in your guidelines, in the guidelines of your Department of Public Works. They list stabilization, which is chemical stabilization using lime. Remember that I told you that the problem is cations, the clays are electrically negatively charged and they want positive charges. Okay, let's give them the positive charges. That's what chemical stabilization does. And essentially, let's give them the positive charges and let's keep the clay happy. And that's what lime stabilization and cement stabilization does. There are some benefits and there are some problems. I'm going to show you some data about chemical stabilization. And the main problems are, unlike other stabilizations, sometimes if you improve the conditions of your road, you improve the conditions, you improved your problem. In chemical stabilization, our experience is either you improve the condition of your road so well to the point that you kill the swelling of the soils, or you still have, sometimes you create a bigger problem than what you had to begin with. I'm going to walk you now through an additional approach. It's an approach that is, I would call it the newest approach. Is the one that is being adopted in the Texas Department of Transportation most commonly these days, along with some chemical stabilization. And the approach that I'm going to tell you about is geosynthetic stabilization. So that is what is going to be the rest of this lecture. I'm going to tell you what is this new approach that potentially you may want to consider. The good news is that a lot of work has been done in Texas, and I'm going to show you that work in order to reach to how to do it and how to do it well. And the objective of this application using geosynthetics in roadways, and here is again the road founded on expansive clays that I can visit are 20 minutes from home. The objective is to retard or eliminate these longitudinal cracks. The problem in itself are the longitudinal cracks. That is we do not notice those changes in volume when you are driving. What we notice is the longitudinal cracks that are the conduit for subsequent degradation of the road. So again, to clarify what the problem is, there are different strategies that we can think of. Why are we dealing with a strategy of stabilization of the base? This is what we're going to do. We're going to stabilize the base using geosynthetics. And why is that going to work? Let me show you. So if we do not have geosynthetics, again, during the wet season in our road, the waterfront is going to advance from the shoulders. And at some point, when the dry season comes back, let's call it a drying front advances from the shoulders. The road is going to heave, or not the entire road, but the portion of the road that is closer to the shoulders is going to heave during the wet season, is going to settle during the dry season. And at the end, I'm going to ask you to check on one thing. When you see new cracks in your road, check. Do you know when they happen? At the end of the dry season. At the end of the dry season, you are going to see that you are going to develop the longitudinal cracks. At what location it depends on how far the drying front advances during the dry season. That's where you're going to have the longitudinal cracks. So it's a ductility problem. It's a trigger. We have strain concentrations that trigger this crack. So essentially what we're going to do with stabilizing the base is essentially we're going to add ductility. Not only the base is going to remain the same lateral restraint that would benefit, for example, to increase the stiffness of the base, which is a good thing. In this case, we're going to do it to increase the ductility of the entire structural package. So the entire road, the region over which this stress concentration could occur is distributed to the point that we're not going to trigger those cracks. This is the strategy in which we have been using this for the last 15 years in Texas. And this is the strategy that has proven to work the best, from the performance point of view, from the economic point of view, from the durability point of view. So essentially, if we have the same problem, the same cross-section, the same weather conditions, the same traffic, but we have this geosynthetic that is stabilizing my base layer, I will be able to avoid the triggering of those longitudinal cracks. So what is the function that we're going to be using? I'm going to call it, the application is going to be a stabilization of the base. We're only going to use one function, and only one.
Okay, and so I just mentioned, sorry, just to interrupt, we've reached 45 minutes. You asked for a warning then. Okay.
Thank you so much.
But it's going very well, so it's very, very nice. Thank you very much.
Okay. I may exceed, just some heads up. If I have to guess, I'm going to go by, Mike, would you tell me again when I'm done with my 15 minutes? And probably I'm going to exceed some 10 minutes or so. Could that be okay?
That'll be fine.
Perfect.
Yep. Yep.
So let me show you what is the Texas Department of Transportation. And this is to the credit of the geosynthetic manufacturers, to be very honest. They say, you should try this, and it worked. So we know that it works, but we need to put it into specifications. And this is the specifications that has been used for the stabilization of roads when the problem is expansive clays, before the revised specifications that I'm going to show you later. The specifications, these are typical specifications, but if you read in between the lines, some of them had to do with the interlocking of that is the interaction that the geosynthetic can do with the soil, with the base material. Some of them have to do with the stiffness, this confined stiffness that the geosynthetics can provide. And it worked. So let me show you some early results. It turns out that Texas was very proactive in trying what they call, they are test sections in which they tried new approaches. And here it is, a geogrid stabilized section, let's call it section 1, in which we know that we're in expansive clays, but there are no longitudinal cracks, but it has a geogrid stabilizing the base. Then we have the same cross-section, the same soils, the same weather, the same traffic, no geogrid longitudinal cracks. Let's do a third section. But not only we have geogrids, but let's have a reduced thickness of the base, no longitudinal cracks. These are wonderful field evidences. So this is just one out of many examples in which the geosynthetic was able to prevent the development of the longitudinal cracks. We were working with the department, we meaning the department, the University of Texas was working with the Department of Transportation in finding ways of clarifying the methodologies and clarifying how this works. And suddenly we get a call. And the engineer from the Department of Transportation tells me, yeah, we're working with a methodology that we have been working with you, but we have not even opened this to traffic. And we already have longitudinal cracks. Oh no, what's going on? Okay, let's go and visit what's going on. Okay, let's do a forensic evaluation. Let's evaluate what's going on. And we excavate, and there is no geogrid. Oh, but actually, people, I was taking a picture of them, and everyone started laughing. And what are they laughing at? Well, it turns out that the contractor messed up because they put a geogrid, but they put a geogrid that was 1.2 meters shorter than what it had to be. So there was a longitudinal crack, but exactly at the location where the geogrid ended. So while you have the geogrid, you did not generate the longitudinal crack. However, as soon as you do not have that geogrid, if anything, this was a perfect validation that the geogrid was working. When you have the geogrid, you do not have the longitudinal crack. As soon as you do not have it, the longitudinal cracks develop. So what is the second lesson that we have from the field evidence? Geogrids appear to work, but if they exist. So if they are in there, they will work. If they are not in there, probably they will not work. Third case history, to spec or not to spec. What about are the specifications that we have been using, are they adequate or not? This is a geosynthetic one that met the specifications, no longitudinal cracks. Another section that also met the specifications at the time, product B, longitudinal cracks. So yes, the geogrid specifications available at the time had not led to a consistent performance. So this led to an important systematic evaluation of the field evidences, including construction of a section where of a new project in which there were 34 test sections, different geosynthetics, different lime stabilization as well, many control sections. And this is just two of the cross sections, and seeing is believing. So what you have here on your left is a geosynthetic stabilized section. And what you have on your right is a control section, no geosynthetic. Again, same soil, same traffic, same weather conditions, same cross section, one with, the other without geosynthetics. Indeed, in this particular project, we used what we now call geosynthetic or geogrid type 1. Type 1 is less sturdy than type 2, which is in turn less sturdy than type 3. But indeed, what we learned is that the average control sections had, what is a measure of performance? A measure of performance in this case, during 1 year of a dry season, in the control sections, we had development of 60% of the length of the test sections developed a longitudinal crack. That was our measure of performance. Someone was not happy. The lime stabilization also didn't show significant improvement in relation to that. I can get into the details on why, but to be fair, the lime stabilization was done, but not as deep as it should have been done in order to do the proper job. But all the geosynthetics that were what we today call a type 1, it's not that they had zero longitudinal cracks, is that they significantly minimized. And this is, again, these are averages out of 34 test sections, so statistically very, very, very strong. And this is a different way of looking at this. So this was a particularly dry season. So going from survey number 14 to survey 18, the control sections increased from somewhere on the order of 8% longitudinal cracks to over 60% longitudinal cracks. The geosynthetic sections went from somewhere on the order of 3% to somewhere on the order of 18% longitudinal cracks. The lime stabilized section went from somewhere on the order of 4% stabilized crack to give or take the same percentage of longitudinal cracks as the control sections. What is the mechanism? So essentially, we have the field evidence. It's unquestionable that we have the field evidence, but we need to understand the mechanism. What is the mechanism? And the mechanism is the mechanism that leads to the stabilization of the base. Let me walk you through what that mechanism is. It's no different than if what you want is to essentially stiffen your base. Why do we have a base? Because we want to transfer the load from the surface to the subgrade. And we want that load to be distributed in as wide of an area as possible. That's the goal of the multi-layered system that we call pavement. Now, it turns out that there is, and I'm not going to get you into the different theories that eventually were evaluated and eventually landed into this mechanism that is the one that makes the geosynthetics work in stabilization, which is the mechanism of lateral restraint. What does that mean? It means that over these cyclic loads, the traffic loads over and over and over, there are elastic deformations, but there are permanent deformations too. The permanent deformations will tend to move these aggregates. This is an aggregate. Confinement is crucial in aggregates. However, so if there is a tiny lateral displacement in this aggregate, is kind of, think of it as a domino effect. A little bit of a displacement in that aggregate leads to a loss in confinement. A loss in confinement in your aggregate leads to a loss in stiffness, and a loss in stiffness in your aggregate leads to this concentration of tension. And we design roads for serviceability. So this concentration in tension leads to rutting, and this rutting is what we eventually call failure of a paved road. How does the geosynthetic work? Well, essentially what the geosynthetic will do is will do several things, but one of them, and very important, is to prevent this lateral movement, this loss of the initial modulus that exists at the time that we build the road. Essentially what the geosynthetic will do, will keep it put, will keep it in place, and essentially will eliminate or mitigate significantly the problem that is caused by these permanent deflections that will occur within the base with the traffic. I'm not going to get too much into how, now that we know how this works, or we think that we know, only now we can come up with a property. And we know that the property needs to be single and relevant, that quantifies the confined stiffness of the sole geosynthetic composite under small displacements. I know that this is a mouthful, but this ended up being a practical and accurate and experimental approach. I'm not going to walk you through the developments that led to the generation of this one property. I'm going to tell you only one thing. This property ended up being what we now call, and I can give you some references on what are the analytical and experimental results that lead to this KSGC. I'm going to call the property the KSGC, the stiffness of the sole geosynthetic composite. But it turns out that in practice, this stiffness is the following. A a measure of the interface, the load transfer, let's call that tau y, times a measure of the stiffness of the product, shear and stiffness. So a high shear transfer that requires good interaction between the soil and the surrounding base. That's necessary, but not sufficient. We also need a good stiffness of the base, of the geosynthetic. So it is not that good stiffness will do the job. A very stiff geosynthetic that doesn't interact well is not good enough. A geosynthetic that interacts enough but is not stiff enough will not do the job. We need a good balance. A good balance. The good products are those that will lead to a good balance between the soil geosynthetic interaction and the stiffness. I'm not going to get into the details on how to validate and quantify this experimental property. I'm just going to show you what the development of this equipment looks like. It turns out that we started doing a large-scale box to quantify the soil geosynthetic interaction. TxDOT, the Department of Transportation, came back to us. How long does it take to get your soil geosynthetic interaction? Just 1 week. They said, go back and give me something that is doable in no more than a couple of hours. So this is the final product. This is called the small soil geosynthetic interaction device, which is essentially mounted in a load frame that is not that different than the one that you would use for a tensile test, that many of you may know. Actually, these grips are roller grips that are no different than the ones that you would use for a tensile test. Instead of a lower grip, is a box that confines the lower portion of the geosynthetic. And you can think of it as the basis of a pull-out test, but really we're not interested in resistance. What we're interested in is on the onset of movement. And that has been documented, a very recent design method, testing procedure by the Texas Department of Transportation. Okay, let's now go and let's see what these test results tell us in 1, in 2, and 3, in 5, in 10, in 13 geosynthetic types. And that's what we did. So here it is. So here we measured the soil geosynthetic interaction, the stiffness of the soil geosynthetic interaction, and they are not, all the products are not the same. Some of them will have a high interaction, or high stiffness. Some of them will have a low stiffness. Well, but where do we have the threshold? How do we correlate with this with the field? But remember, in Texas, we had a mine gold in field data that tells us, because they have test sections that compare sections with and without geosynthetic. So this is what we can do. We have now the quantification of the property that may govern this stabilization of the base. So we take this to the field. And let's go back to the FM2. FM2 was that one that I showed you that showed 34 test sections. We have 3 geosynthetics. The KSGC was on the order of 10. The 3 geosynthetic sections were considered adequate. The control section was considered not adequate. Let's go to another one. This is SH21. SH21 is a different case history that has geosynthetic 1 and geosynthetic 7 and geosynthetic 10. Different KSGC, different measures of performance. The control section did not perform. Let's go to another site. FM, this is a road in Texas, FM 1644. Control section, the geosynthetic stabilized section did work. The control section did not work. Let's go to another one, Cabeza Road. Geosynthetic 7 worked. Geosynthetic 9 did work. Control section did not work. And remember that we had that one in which we had 2 geosynthetics, one that worked, the other that didn't work. Okay, the geosynthetic that worked, well, this is the KSGC. The geosynthetic that didn't work, this is the KSGC. That performance was inadequate. Another one, remember that I showed you another case in the very beginning when we were collecting evidences of geosynthetics that sections that did work. Here it is. Geosynthetic 1, KSGC that was considered adequate, the control section that was considered inadequate. Even a roadway with a reduced section was also considered adequate. So now is that we have completed the cycle. We have the field evidence. We developed the theory to understand the mechanisms. We developed the property, and I recognize that I did not tell you much about the property. At this point, I'm going to tell you, trust me, we developed the property. But then we went back to the field and correlated that property to the performance in the field. And here is what eventually is leading now to these new specifications by the Texas Department of Transportation. Yes, we have the KSGC, the stiffness of multiple geosynthetics, but more than that, we also have measures so we can define based on field performance what we're going to consider failure, non-acceptable, and what we're going to consider acceptable. But more than that, not all geosynthetics are the same. Some of them, let's call them type 1. Some that are okay, let's call them type 1. Some that are really good, let's call them type 2. Some of those that are excellent, let's call them type 3. And we can do that because we have field performance to associate to the experimental data. And that is essentially what we have developed. And essentially, that's why not only we're going to distinguish between what is adequate and what is inadequate in terms of properties of geosynthetics, working on stabilization, but also among those that are acceptable, which ones are great and which are just okay. So the specifications, and I'm showing you here again, the original specifications from the Texas Department of Transportation was modified in two ways. One that establishes what is the stiffness of the soil geosynthetic composite, what is acceptable, and what is not acceptable, and among those acceptable, what are different levels or types of geosynthetics, and even more. The Department of Transportation was courageous enough to say, do you know what? If there are excellent geosynthetics, let's go for them, but let's distinguish them from the good geosynthetics. So they created a type 3 among the geosynthetics used for stabilization. I know that I did rush and I only showed you for a very light version of some of the data. All this is public domain. It is available. It is in a report by the Texas Department of Transportation. And this is the access that you may have to that document with the field, the lab, and the analytical developments. So to conclude, I gave you initially a brief overview on why this is a problem. I gave you some information that I collected from the excellent work that the Department of Public Works in Indonesia did. And let's agree that we do have a problem in the US, we have a problem in Texas, and we may have a problem in Indonesia. Now, how to solve that problem? Here are some of those conclusions. The confined, and this is the research part of those conclusions. The confined stiffness of the soil geosynthetic composite was identified as a relevant property. It's not necessarily the only property, but this was a relevant property. A new soil geosynthetic interaction testing device was identified to quantify that property. And this parameter is a unique parameter in the sense that it adequately characterizes in a single shot both a product that has the adequate interaction, that provides the adequate interaction, and provides the adequate stiffness. The use of geosynthetics was found to effectively minimize the detrimental effect of expansive soil subgrades. And frankly, this is, I would say, the solution, the approach. There are several approaches to address problems associated with roadways in expansive clays. This is probably the one that is being adopted the most frequently in Texas nowadays after this series of demonstrations. Field data, very important field data, hard to get field data. Serviceability data has been shown to has proven to show a beneficial effect of geosynthetic stabilization, with the field performance correlating very well with the magnitude of the parameter that we have identified. And the Texas Department of Transportation has successfully implemented the KSGC into specifications for large projects. As final remarks, the overall geosynthetics have been demonstrated to improve often significantly the performance of roadways. And the state of the practice is rapidly improving as new research is identifying the properties that govern the impact of geosynthetics in roadway stabilization. And with that, I thank you so much for your attention. And I'm going to stop sharing. Mike, back to you.
Yeah, sorry. There we are. Okay. I think I'm on with sound and the video. Okay, Jorge, first of all, I'd say that was a wonderful presentation. You did exactly what we asked you to, which was to outline the problems, to demonstrate how this exists in your own experience, and then relate it to that information from Indonesia, which was brilliant, and then to look at solutions, and of course the solutions are what engineers are after. So wonderful presentation and incredible information. We have a fairly active Q&A, so I think the best thing to do is I've been reading them as they come in, and we have some very good questions. So I would perhaps specify if I read them to you, and then if you could help with your own opinion on the answers. So
okay,
I'll go from the top. You can probably read them as well, I think. But we start off with from Astrid, who actually was she introduced our webinar earlier on, and she thanks you for the presentation. But one quick question here was, when is the best time to install the geosynthetic, at swell condition or shrink condition? Is an interesting question.
Very interesting question. Typically, we have no choice on that. In Texas, at least, we have a construction season, and wherever that construction season is, that's where we're gonna be installing it. If I have the ability to dictate the sequence, and remember that construction typically takes several months in a roadway, so it is not that we're gonna install it in a given week. So we're talking about sometimes long periods. But for that excellent question, I would say that the ideal situation would be to install it during the dry season, because the swelling is not the one that leads to cracks. So if you install it already during the dry season, it will the site will primarily swell, and the shrinkage will not shrink beyond the initial condition. Excellent question. Maybe we need to implement this. Who did ask this question?
Well, Astrid, yes. Actually,
okay, that's an excellent suggestion. And actually, you kept me thinking. We have never played with a recommendation like that, but maybe we should. Considering that's the advantage of identifying the mechanism and not knowing, yes, it did work in the past, it will work in the future. Even if we didn't use the fact that played with the construction season, I'm convinced that if you install them during the dry season, you are going to have a better performance than if you do it during the wet season. Excellent question. Excellent question. Thank you.
Thanks, Jorge. Let's move on. Next question from Kianush Hatami. This is related to the centrifuge testing you mentioned. To what extent is the soil permeability changed by the centrifugal force relative to the 1G condition? And how is that change accounted for in interpreting the results?
The change is zero. And we have data to show the changes in centrifuge test versus non-centrifuge test. Janusz, what you need to think of, essentially what we're doing is we're imparting a gradient. When you do a permeability test, a hydraulic conductivity test, you impose a gradient, but it's a gradient, because you're in saturated conditions, you impose a gradient in pressure gradient. What the centrifuge does, it imposes a gradient, but it's a gradient in elevation potential. That's the only difference. So the only thing that we do whenever you calculate the head, the hydraulic head, in a conventional permeability test, hydraulic conductivity test, you impose a gradient. You mess up with the gradient in your sample, but you mess up by placing a pressure head, a pressure gradient, a pressure difference. In this, you also create a gradient, but it's an elevation gradient. Think of it as we simply add confinement. And we need to take into account deformability and all those aspects. But the important thing is at the moment of testing, at that time, once we're spinning, do we know the void ratio? Do we know the gradient? And if the answer is yes and yes, and we do, then we can calculate the hydraulic conductivity. There's no scaling loss in the particle size or in the hydraulic conductivity in this particular case.
Well, thanks, Jorge. It's a relief to hear that. Difficult topic. Yeah. Next question, another interesting one from Justjan Harry Suprapto. He says, very interesting presentation, Professor Zornberg. I have a question. Is there any correlation between the high swelling value to the concentration of montmorillonite based on visual observation using SEM?
That is an excellent point. The answer is certainly yes. And but SEM will only tell you if you have clays. The quantification of the different minerals that you have is an important approach. Is an important approach, certainly better than the approach of using Atterberg limits. So if you want to know if you have a problem, one way is let's get the Atterberg limits, let's get the activity, let's get the mineralogy. You are getting closer and closer to the problem, but you are still shy of quantifying the swelling. The reason that it swells is because we have the smectites. To quantify the swelling, I can think of no better approach than measure the swelling. So that is the approach that we're doing. If we want to know what the swelling is, measure the swelling. Yes, we can get excellent correlations. One would be with Atterberg limits, with activity, with mineralogy, but those could be correlations to get the swelling. If we can measure the swelling, our approach was let's get the swelling, and that's what we ultimately need. To calculate the PVR, what you need is a relationship between swelling versus confinement. And we measure the swelling, we measure the confinement, we get the relationship. But it's certainly a very good approach.
No, good. That's very interesting. We have some more questions from Kianush Hatami, and also very interesting ones. So first one is that the text.specs seem to have only focused on geogrids and their required properties. Has there been any work on using newer geotextiles as well to see if they could also be effective?
That's a very, very good question, Kianush. The property that we are measuring, I could say that is blind to the type of geosynthetic, because we measure a confined stiffness, a combination of a confined stiffness and an interaction. Now, the interaction can come in different ways, and geotextiles have a different way than geogrids, but both of them interact with the salt. So the property that I'm measuring is I could call it a more generic property. The specifications are not. The specifications are not because this property was added to existing specifications, and the current specifications essentially try to mimic, because they had to be generic. Okay, what do we know about the products that do work different than the products that didn't work? And yes, they were shooting in the right direction. And I mentioned interaction, and I measured stiffness, but the measures or the qualitative measures of interaction in a geogrid are going to be very much based on aspects such as aperture sizes and geometry. In a geotextile would be different. So these specific specifications, and also, frankly, it was based on they were based on past experience, and the past experience in Texas is significantly higher when using geogrids than using textiles, for example. I believe that both of them can develop excellent. The experience is higher, at least in Texas, with geogrids, and that is kind of reflected in the specifications.
Well, thank you again for that. I'm not sure on our timing, so we have quite a few more questions, Jorge, and they're growing at the moment. So I'll carry on. I'll go down the list in order, and then the organizers can always tell me if we've reached our time. But one more. This is also from Kianush. I think quite an interesting one. It says, could you comment on the combined use of geosynthetics and chemical stabilization in some roadway projects? To what extent and in what ways could geosynthetic stabilization be effective on subgrades that are chemically stabilized already?
That's an interesting question. I have some examples. I cannot give you a final answer. This is our experience. I'm not going to tell you a thorough evaluation. I'm going to tell you on the experience. I showed you a case history, at least one, in which the use of lime stabilization did as poorly as control sections. In that same test section, in that same project, we had sections that had both lime stabilization and geosynthetic. Guess what? The geosynthetic section performed better than this section with geosynthetic and lime stabilization. Our interpretation is the following, and this is an interpretation. I cannot give you a conclusive answer. The practice of using lime stabilization, because going deep enough to kill the swelling is too much, it's too expensive. The practice is saying, do you know what? Just stabilize the top. And when you stabilize the top, let's say 4 inches, 10 centimeters or 15 centimeters, stabilize that. But you are not going all the way, and the top 10 or 15 centimeters you kill the swelling on that top fraction of the subgrade, but the lower fraction still swells. So it's going to swell overall. The swelling is going to be less, but now you have a problem. Before, you have swelling and a ductile soil, and the geosynthetic adds ductility. And now we have less swelling, but a brittle crust. And we attribute the potential, at least our observations in that case history, and I don't want to generalize, is that what happened if you have chemical stabilization, but not of the enough complete stabilization, is that you may have the risk of creating a brittle crust that will not swell, but if there is swelling below that crust, now that crust is brittle, and you do not want, if what you want to prevent is longitudinal cracks, cracks and brittle materials do not get along well. So that is our explanation for those evidence. I don't want to generalize, but that has been our observation in at least a couple of cases. Excellent question.
Right, thank you, Jorge. We've been given about 10 more minutes, so I think we can probably cover most things. A quick question here from Ibu Astri again. How to define crack percentage? Well, this is an interesting point.
Yeah, it was defined the following way. And I'm going to try. We had protocols, and I can give you the protocols. This is not a standard measure of condition survey. So essentially, what we were doing was a condition survey, and the Texas Department of Transportation has very well established protocols for condition survey on roadways. However, they go after distress that is typical of traffic distress. But this is a different type of distress. So we characterized a percentage of longitudinal cracks as by measuring the length in a given control section, in a given section. Let's say that the section is 100 meters or 150 meters. In that section, how long are the cracks? And we used a protocol that was longitudinal cracks that exceed 3 millimeters in width. So when I say that I have 20% percentage of cracks, means that the length of all the cracks put one behind the other is 20% of the total length. We have sections in which we have 200% longitudinal cracks. That means that we have more than one crack going parallel and over the length. So it's a reasonably straightforward, I would say, very well-defined, but I would say new measure of performance, strictly focusing on longitudinal cracks that we identified as being the fingerprint of the problems associated with expansive clays. Clays are always bad, and clays can also lead to other types of distress, but we focus on that as being the one measure that we could track very consistently.
Yeah, thank you, Jorge. Okay, so next question is from Pak Go Chi Leong. Pak Go, he was our previous INA-IGS president. He's actually got 3 questions in here, but they are linked together. So, so how to assess the effective high of the confinement induced by geogrid? I think basically they're assessing confinement and its quality, if you like. Any experience on geocell? And the third question is, can Girouhan or the Pokhara method be used in the design of roads on expansive soil? Probably we have also to check against the potential swelling pressure of the expansive subgrade.
Very, very good questions. So let me go one by one. The first one was
basically, I think assessing the quality of confinement.
Okay, that is, we do not measure the confinement. Measuring pressures is very, very difficult in an experimental, in a field setting. I may have some measures to tell you. We have a major field monitoring program that is going on right now, and we expect to give you some hard data on lateral restraint, on some measures of confinement, some measures on changes in strain. Pressure is very difficult, but we will attempt to do it. So what we do have the most is measures of straining that occur, changes in pressure that may occur because of the strains that develop with time. Assuming, if we need to assume what is the initial confinement, then we can give you some answer. Hopefully, I do not have hard data to give you. Hopefully, we will. The second question was about geocells. Yes, geocells could, in principle, do an excellent job in lateral restraint, which is essentially the basis of why this would work. We do not have data on that, but I'm just telling you my assessment based on my understanding of the reasons that lead to a good performance is any approach with geogrids or with geocells that lead to stabilization of the base, which is no different than the stabilization that we try to obtain when our objective is to increase the stiffness of the base, will provide the ductility that you need to mitigate problems associated with expansive clays. The Girouhan approach I couldn't use that, not because it's bad, but the Girouhan approach is an excellent approach for a different type of stabilization, that is stabilization of soft subgrades. In this case, we are not necessarily confronting soft subgrades. We're confronting, so essentially the Girouhan approach tells you within the subgrade itself, are we away from failure in the subgrade, not in the base? It is true that the Girouhan approach has some measures of what happens in the base. And if you're familiar with the system, with approach, there are some measures of the angle of distribution. But at the heart, the Girouhan approach measures how to handle essentially the thickness of the stabilizing platform that you need in order to handle a soft subgrade problem. So it's a different problem. It's a different problem. I could say that it's much closer to the problem of blanket stabilization of the base that in the US is addressed using methods such as TBR or CBR that is strictly based not on, it doesn't assume significant deflections. It assumes that essentially you are stiffening the base. The Girouhan approach assumes that you can develop comparatively high vertical deflection, so uses mechanisms that are beyond the ones that we use just when we want to stabilize the base. But excellent question.
Okay, Jorge, thanks again for that. Right, we actually have a number of questions on the KSGC parameter. So the first one is again from Pak Go, same person just now. Please explain once more on how to measure the KSCJ. Now, if you think that's going to take too long,
Yeah.
we are going to ask you for if you can kindly provide a PDF copy of your material later on. So I guess people can get it from that.
Yes, that is true. I didn't get into that. At this point, I didn't show you experimental data. I didn't show you the analytical development. I didn't show you consistency of the results. I didn't show you that. I just told you we developed a methodology based. There is an analytical background. There is an experimental background, but I didn't present it. So I can give you the literature on that. Definitely.
So could you do that? Maybe we could add that a link to that in
Absolutely.
the follow-up. That's fantastic.
Absolutely.
Thank you. Okay, and now another. Oh, we have a question here from Malaysia, from Tony Barry, someone we know very well who's worked a lot in Indonesia, but now he lives in Malaysia. And does the KSGC value, does it correlate with cost? There's an interesting one.
Yes, as anything. So think of the KSGC as a measure of, there's a mouthful, is the stiffness of the soil geosynthetic composite and their low displacement. So think of it as not the stiffness under not the confinement of soil in isolation. Is confined, so it takes into account the interaction that occurs with the soil, but it's essentially the way that we measure it, and comes back to the previous question, how we measure it. We need to identify if you are loading a geogrid that is confined within the soil. Essentially, you have the displacements that are occurring first in the beginning at the point of application of the load, then later into the geosynthetic, then later into the geosynthetic. Eventually reaches the end of the geosynthetic, and that's what we would call pull-out failure. We're not interested in pull-out failure. We're interested at the moment, let's call it a loading front. At the moment that the loading front reaches a point, what is in the next increasing in load, what is the stiffness at that point? That's how it's measured. And I'm not sure if I answered the question or not, but
correlate with cost. Yes.
Correlate with cost. I would say that the products that have a higher, you need a good balance between interaction and stiffness. And that measure gives you both at the same time, and is a balanced relationship. Now, products that are going to interact better and they are going to have stiffer, typically are going to have higher mass of polymer, and typically are going to be more expensive. So yes, it's a measure at the same way that, I don't know, for reinforcement application, walls application, higher tensile strength is typically associated with higher cost. Why? Because these are more robust materials, use more polymer. In this case, it's always could be the case, correct. But it's not the only aspect. Mm-hmm.
Right, thank you, Jorge. Okay, this is from Kianush again. Have there been any similar studies on the efficacy of geosynthetics in rigid pavements? I'm not sure it's quite direct, but is that something you've looked at over swelling soils?
Not with this approach. That's a great topic. I am guessing that there will be an impact. We do not have the data. Why I'm saying that it matters, because even if your design calls for a base and you ask that base to be stiff, and I'm not talking about expansive clays, I'm talking about strictly structural capacity, then a base with geosynthetic and a base without geosynthetic have different stiffness. And consequently, if your concrete paved road it needs some stiffness coming from the base, it will improve. But I have no data on that. But that's a good point.
Yeah, well, thank you. You're doing extremely well. I think we can just about fit things in the last 2 or 3 minutes. But this is from Uma Shankar. Very nice presentation. Is anchorage length needed beyond the shoulder, or can it be just right at the edge of the shoulder of the road?
That's a good point. That's a that's a performance issue. Think of the length that you want as the length where you can live without a crack. You can assume if it is a highly expansive location, whenever you do not have the geosynthetic, the geogreen in this case, and that's the example that I showed you, you should not, you have no protection about the development of longitudinal cracks. The main problem with longitudinal cracks is being a conduit of water within the paved portion of the roadway. If you can live in the shoulder with cracks, then I could say then there is, you do not need to extend beyond the, let's say, the white lane of your road. If you want a good performance in your shoulders, then you should extend the geogrid as well. So if you don't want longitudinal cracks, the geogrid should be there.
Right, I think we just have time for one more. There is a question from Arlene about, it's all about the KSGC, and I think that's going to be covered by additional documentation. So I'll just go to a final question from Pak Gochi Leong again. And this says, do we have to limit the strain of the geosynthetic to less than 3% in order to guarantee the performance?
We do not do that. Let me tell you how that has to do with how the measurement of the KSGC is, because we need a initial stiffness. But what is initial stiffness? And in our testing protocols, we define initial stiffness as the load that is developed in our testing procedure when the displacement, not the strain, when the displacement is 1 millimeter. At that point, we define the stiffness, and we found that this is essentially large enough that we do have good resolution of our displacement measurements, but small enough that doesn't get into any large displacement considerations. So what we really want is the initial stiffness. So the specifications may call for that, but that's above and beyond requirements that you would put based strictly on the KSGC. For the KSGC, and this is a protocol, and again, it is a combination of what is measurable with what is necessary. We measure the stiffness at a displacement in the device at the point under the confinement of soil. Once that point displaces 1 millimeter, boom, that's where we measure the stiffness. That's our protocol. We have seen that the curves, we generate curves, and these curves need to be linear, and the linearity is way, way beyond this 1 millimeter. So we're confident with that. And we have not tested, we have tested many products, but none of them so far are at this level of displacement, none have shown any nonlinear response. So we're confident with that, at least with many products, but we have not tested all the products.
Jorge, thank you very much. Well, I'm going to let you rest now. That was, I would like to thank you myself for an incredible presentation. You've given us a wealth of knowledge and information in that. And I think anybody who gets involved in construction of roadways over expansive soils, and there must be quite a few people here, I think you'll have helped hugely, both in understanding the problem and looking at solutions. So thank you very much again from me, also from dealing with a huge list of questions at the end there very, very effectively. I hope you might stay on with us to listen to the quiz, which is coming up in a minute. But I also would again like to thank the organizers for arranging this today. And I will hand back to Rifa and ask her to carry on and take us through the final parts of our webinar.
Okay, thank you, Pak Mike. Once again, thank you, Professor Jorge Zornberg, for your excellent presentation. And thank you also to Bapak Michael Doby for guiding the session. Next, I would like to invite all of you participants for the chance to get the very interesting prize of the total of 250,000 rupiah by joining a very short game we have prepared. This quiz is also prepared by the questions for the quiz also prepared by Professor Jorge Zornberg. And the first winner of this quiz will get 150,000 rupiah, and the second winner will get 100,000 rupiah. To give you a disclaimer before we play, everyone can join this quiz, but for technical reasons, only those who live inside Indonesia are eligible to get the prize. You can now directly go to your browser on your phone or your PC and type menti.com, menti.com, menti.com. You have to type the code number shown on your screen or also there in the chat box, and the code is 11019230. Once again, please go to menti.com and put the code 11019230. Then fill in your name and make sure it is the name that you submit in the registration for this webinar. Or if you forgot what you type on the registration page, you can see your display name right now. So later, if you win the game, the committee will easily contact you for the prize. Remember, the prize is very interesting. We have the total of 250,000 rupiah, and you will not want to miss this chance for those who live inside Indonesia, especially. So go to menti.com, put the code 11019230, and fill in your name. So, okay. Type menti.com on your browser. You can play it on your PC or you can play it on your phone also, and insert the code 11019230 and input your name as registered on your Zoom webinar, or you can see on your display name on the Zoom right now. Let me share the game now. Wait. Let's see. We have 71 participants. We will wait for another minute. You still can join and win the total of 250,000 rupiah. Everyone can join this game, but for technical reasons, only those who live inside Indonesia can get the prize of 250,000 rupiah total. So the first winner will get 150,000 rupiah and the second winner will get 100,000 rupiah. We have 77 participants. We will wait 15 more seconds. I'll start the countdown. 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. We will start the game now, starting with the first question. Answer fast to get more points. The estimated total annual damage from expansive clays in the US is, first option is negligible, second option is approximately $1 million US, or is approximately $1 billion US, or exceed 15 billion US dollar. You have roughly 25 seconds to answer. Is it the first option? Is it the second option? Is it the third option? Or is it the fourth option? The estimated total annual damage from expansive clays in the US. So you have 8 seconds. 5, 4, 3, 2, 1. Time's up. Let's see. The correct answer is the fourth one. Exceeds 15 billion US dollars. Let's see who actually leads the first leaderboard. For the first question, Wong Tianming leads the leaderboard for the first question. Everyone, you guys still have the chance to win this game. There are 2 more questions. Let's start with the second question. Brace yourself. Second question. Answer fast to get more points. Important properties that should be considered in geosynthetic selection to stabilize roadways over expansive clays are, first option, geosynthetic tensile strength, or second option, geosynthetic stiffness. Third option, geosynthetic interlocking, load transfer capabilities. Fourth option, properties listed as 1 and 2 above. Or fifth options, properties listed as the second option and third option above. Or six, properties listed as 1, 2, and 3 above. There are many options you can choose, but choose wisely. 10 seconds. 5, 4, 3, 2, 1. Time's up. Let's see the correct answer. It's the fifth option. Only 9 people get it right. The properties listed as the geosynthetic stiffness and also the geosynthetic interlocking load transfer capabilities. Let's see who leads the leaderboard for the second question. So many options. Oops, wait. There are technical. No. Wait. Have technical. Sorry for that. Let's see. Okay. Let me share it again. So, who leads the leaderboard for the second question is oops. Let's see for the second question. The fastest one is Ignatius Tommy Pratama, but who leads the leaderboard is Arik. Last question. Question 3. Answer fast to get more points. The Texas Department of Transportation has adopted base stabilization with geosynthetics for roadway over expansive clays because, first option, geosynthetics have been used in these applications for over 50 years. Second, field demonstration prove performance of geosynthetic sections. Third option, limit equilibrium studies showed high FS with geosynthetics. Or the fourth option, geosynthetics minimize moisture fluctuations in expansive clays. Is it the first, second, third, or fourth options? You still have the chance to win the game. 10 seconds left. 5, 4, 3, 2, 1. Time's up. So the correct answer for the third question is the second option, field demonstrations prove performance of geosynthetic sections. Okay, let's see who in the game. Only 2 winners. So congratulations to Ignatius Tommy Pratama with 2,671 points. You will get 150,000 rupiah, and the second winner with 100,000 that will get 100,000 rupiah is Arik with 2,602 points. So congratulations to Ignatius and Arik. And also thank you for everyone who joined the game. Ladies and gentlemen, we invite you to the upcoming webinar under the theme Capillary Barrier System CBS and Geobarrier System GBS for slope protection against rainfall. And we'll be speaking in this webinar is Professor Haryanto Raharjo from Nanyang Technological University, Singapore. The webinar will be held on September 22nd, 2021 at 6:30 p.m. GMT +7 or Jakarta time. And for the upcoming webinar, the presentation will also be delivered in English. You can register at the link as.id/webinar INA-IGS 09. You can also see on the chat box and on your screen. And ladies and gentlemen, we have now reached the end of the event. Before you leave this webinar, we would like to inform you that you can access your e-certificates and also the soft copy material from the speaker by visiting the link as.id/info INA-IGS08. And after filling the quick survey, you will be redirected to the e-certificates. So after you leave the webinar, you will also automatically be redirected to the survey, so don't worry, or you can also click on the link on the chat box. So ladies and gentlemen, once again, thank you for your participation. We thank you, the speaker, Professor Jorge Zornberg, also our moderator, Pak Mike, and also Ibu Asri that already opened our event. And we hope we can see you at the next event. Finally, good afternoon and stay healthy, everyone. Thank you.